At the heart of the galaxy, Holmberg 15A lies one of the most colossal black holes ever found, so massive it breaks our models of how galaxies should form. Its gravity shapes everything around it, yet its true nature remains a mystery. Tonight, we'll explore why this object challenges everything we thought we understood. If you enjoy this journey, please like, subscribe, and share, and tell us in the comments what's the first question you would ask about a black hole, this enormous. Thank you for watching. Now let's begin. Far from the Milky Way, a massive congregation of galaxies sits in space as a single bound structure, known as the Abell 85 cluster, held together by gravity over a region that spans several million light-years. A galaxy cluster is a large-scale system in which hundreds of individual galaxies, together with hot, thin gas and an even larger amount of invisible dark matter, move within a shared gravitational well. In Abell 85, this shared well is deep, so that galaxies travel through it at speeds of many hundreds of kilometers per second, while the cluster as a whole lies at a distance of about 700 million light-years, far enough that its light left long before the Earth formed. The view in visible light shows a crowded field in which many small faint smudges and several larger brighter ellipticals and spirals are scattered across the frame. But this visible scene is only a fraction of the total contents. Filling the space between the galaxies is intracluster gas, a very thin plasma that is so hot it shines mainly in X-rays rather than in ordinary light, with temperatures of many tens of millions of degrees Celsius. This gas traces the gravitational potential of the cluster, pooling most densely near the center and becoming more rarefied toward the outskirts, so its glow reveals where the cluster is most massive. The presence of such hot gas means that Abell 85 has had enough time to form and settle, because material falling into the gravitational well is heated through shocks and compression until it reaches a roughly stable temperature and distribution, even though individual galaxies continue to move through it. Each galaxy follows its own orbit through the cluster, sometimes passing relatively close to others and feeling additional gravitational pulls that slowly change its path. Over billions of years, repeated encounters and the global pull of the cluster can strip stars and gas away from galaxies, adding their material to a diffuse background of light and to the intracluster medium. Smaller galaxy groups that fall into Abell 85 along the surrounding large-scale filaments bring in fresh members and material, which are gradually mixed into the cluster population. In the outskirts, where the pull of the cluster is weaker, galaxies may still retain much of their own gas and show ongoing star formation, while nearer the center the stronger gravitational tides and the hot ambient gas tend to remove cold gas and slow down star birth. The dark matter that dominates the total mass of the cluster is not seen directly, but its presence is inferred from the high speeds of the galaxies and from the amount of a hot gas required to fill the potential well. When astronomers map the positions and motions of the galaxies, and when they measure the brightness and temperature of the X-ray emitting gas, they find that the total mass far exceeds what would be expected from visible stars and gas alone, pointing to a dark halo that outweighs the luminous matter by a large factor. This combination of galaxies' hot gas and dark matter gives Abell 85 its overall structure, with a dense, bright central region, surrounded by a more diffuse extended halo of member galaxies. The cluster is not perfectly smooth. Substructures such as smaller subclusters and infalling groups are present, leaving traces in the distribution of galaxies and in subtle variations of gas temperature and density. Shock fronts in the gas and regions where the temperature changes more sharply tell of past mergers between smaller systems that have combined to form the present cluster. On very large scales, the galaxies trace out a three-dimensional pattern that is still being assembled, as material continues to flow in from the surrounding cosmic web, feeding the cluster through long, tenuous filaments. Within the cluster, individual galaxies range from gas-rich spirals with prominent disks and arms to smooth ellipticals whose stars follow more random orbits, and this mix reflects the different formation histories and environments they have experienced. Interactions with the hot intracluster medium can strip gas from the disks of galaxies that move rapidly through it, leaving behind long, faint trails and gradually changing blue star-forming systems into red, more passive ones. Close gravitational encounters between galaxies can disturb their shapes, trigger short bursts of star formation, or in some cases lead to mergers that build larger systems from smaller building blocks. Over time, these processes redistribute stars and gas throughout the cluster volume, and they help to establish a population in which many galaxies near the center are massive, smooth, and relatively old. Multi-wavelength observations add further detail to this picture. In radio wavelengths, astronomers detect emission from jets and lobes powered by central engines in some cluster galaxies, which inflate bubbles in the surrounding hot gas and gently heat it. In X-ray images, the intracluster gas appears as a glowing atmosphere that extends far beyond the region where most galaxies are seen in visible light, confirming that the cluster's luminous galaxies sit within a much larger reservoir of hot plasma. Gravitational lensing, the subtle bending of background light by the cluster's mass, provides another way to weigh the total contents, and studies using this effect reinforce the conclusion that dark matter dominates the mass budget. Taken together, these observations show Able 85 as a mature, massive cluster in which hundreds of galaxies, an expansive envelope of hot gas, and a dominant dark matter halo all share the same deep potential well. Within this environment, the gravitational center of the cluster is marked by a particularly luminous galaxy that sits close to the bottom of the potential well, and the surrounding swarm of galaxies, gas and dark matter, all respond to this shared center of mass as they move on their long orbits through space. Within the Able 85 cluster, the many individual galaxies and the hot intracluster medium together form a complex environment in which gravity, gas dynamics and radiation all play important roles over long timescales. The galaxies are not scattered at random but follow the same overall gravitational potential, defined by the cluster's dark matter halo, so their velocities and positions trace out the shape and depth of the potential well. In the projected view on the sky, astronomers see a crowded arrangement with more galaxies near the center and fewer in the outskirts, and this projected crowding reflects a three-dimensional distribution in which galaxies move along orbits that can be elongated or more circular depending on their histories. Massive elliptical galaxies are more common near the central region, where repeated mergers and close encounters have transformed earlier disk galaxies into smoother systems with little cold gas, while further out spiral galaxies with visible arms and disks remain more frequent. Each galaxy carries its own stars, gas and central mass, but as they travel through the cluster, they interact with the intracluster medium, the very hot plasma that fills the space between them. This gas is extremely diffuse, with densities much lower than the best vacuums produced in laboratories on Earth. Yet on cluster scales, it contains more mass than all the gas inside the galaxies themselves. Its temperature reaches many tens of millions of degrees Celsius, so its atoms are stripped of most electrons, forming a plasma that emits X-rays through thermal processes such as Bremsstrahlung radiation and line emission from highly ionized elements. When X-ray telescopes image Able 85, they reveal a smooth but not perfectly uniform glow that extends well beyond the visible cluster core, showing that the gas atmosphere reaches out for several million light-years. The brightness of this emission decreases with radius, marking how the gas density falls off away from the center, while changes in temperature and brightness with position provide clues to the cluster's dynamical state. Regions where the temperature rises sharply, or where edges appear in brightness, maps can indicate the presence of shock fronts which form when gas from an infalling subcluster or group plows into the existing intracluster medium. Such features record the history of past mergers and ongoing accretion, and in ABEL 85 studies of the X-ray morphology point to a system that has experienced interactions and is still being assembled even if its central region appears relatively relaxed. The galaxies moving through this hot medium experience ram pressure a force exerted by the gas as a galaxy's own interstellar medium collides with it at high relative velocity. When this pressure exceeds the gravitational binding force holding gas to the galaxy's gas can be stripped away, leaving long faint tails of gas, and sometimes young stars behind. Over time, this process reduces the supply of cold gas available for star formation in many cluster galaxies, especially those that spend long intervals orbiting through the dense central regions. As a result, the cluster population is often dominated by red passive galaxies, with older stellar populations and low current star formation rates. Some galaxies, however, still show signs of activity either through residual star formation or through outflows powered by central engines that drive jets of relativistic particles out into the intracluster medium. In radio observations, these jets appear as narrow, elongated features that sometimes bend in response to the pressure of the surrounding gas and the motion of the host galaxy. Their energy input into the intracluster medium helps to counteract radiative cooling of the hot gas, which would otherwise cool and condense toward the center on timescales shorter than the age of the cluster. The balance between cooling and heating, often referred to as a feedback cycle, plays a key role in maintaining the structure and temperature of the intracluster medium. In ABEL 85, detailed observations of the X-ray gas combined with radio maps of jet activity in some central and non-central galaxies allow astronomers to estimate how energy and matter circulate in the cluster environment. The chemical composition of the gas also carries information about past events. Heavy elements such as iron, silicon, and oxygen are produced in stars and released into space through supernova explosions and stellar winds. Over billions of years, these products are transported out of galaxies and mixed into the intracluster medium, so measuring the abundances of these elements in the X-ray spectrum provides a record of the integrated star formation and supernova activity of the cluster's galaxies. In ABEL 85, as in many clusters, the intracluster gas shows significant enrichment in heavy elements, which confirms that numerous generations of stars have lived and died in the member galaxies, contributing their processed material to the wider environment. The distribution of heavy elements is not completely uniform. Modest gradients and local variations suggest that metal-rich gas can be transported by bulk motions, sloshing of the gas in the potential well, and outflows driven by central engines. The galaxies themselves follow orbits that may carry them from the outskirts to the inner regions and back again, and their trajectories are influenced by both the smooth cluster potential and by local gravitational encounters with other galaxies or small groups. Over many orbital periods, these interactions redistribute orbital energies and angular momenta, slowly evolving the overall distribution of galaxy types with radius. In the outskirts, infalling galaxies can still form part of smaller groups which may remain coherent for some time before tidal forces of the main cluster disperse them. As such groups fall in, they can bring subclusters of galaxies and localized enhancements of intracluster gas, which then merge into the main cluster structure. The continuous arrival of such material from the surrounding large-scale structure means that although Abel 85 is dynamically mature, it is not static, but instead is still growing and evolving. Across this environment, the interplay between galaxies and the intracluster medium shapes the observable properties of both. Stripped gas trails faint diffuse light from stars removed from their original galaxies, and the smooth X-ray emitting plasma together testify to ongoing exchanges of matter and energy. The gravitational potential that binds the cluster keeps these components together, but within that overall framework, the details of gas flows, heating and cooling, and orbital evolution of galaxies continue to change with time. On scales of hundreds of thousands to millions of light-years, the cluster environment provides a broad stage on which processes driven by gravity and gas dynamics transform galaxies, establish the hot gas atmosphere, and slowly rearrange mass and energy. Within this broad setting, the density of galaxies and gas gradually rises toward the center of the potential well, where the cumulative outcome of many interactions and mergers is recorded in the cluster's light and gas distribution. Near the center of the Abel 85 cluster, where the density of galaxies and hot gas is highest, one galaxy stands out in brightness and size when seen in visible light. This galaxy is Holmberg 15A, and it lies close to the bottom of the shared gravitational well that binds the cluster together. Astronomers refer to such a dominant central system as a brightest cluster galaxy, meaning that among all the galaxies in the cluster, it is the most luminous in visible wavelengths, and usually also one of the most massive. In Abel 85, maps of galaxy positions on the sky and measurements of their distances along the line of sight show that Holmberg 15A sits near the centroid of the galaxy distribution, where the number density of cluster members peaks. When X-ray telescopes map the hot intracluster gas, they find that the brightest part of the X-ray emission also lies close to Holmberg 15A, indicating that the galaxy coincides not only with the projected center of the galaxy population, but also with the deepest part of the gas atmosphere. This alignment of the central galaxy, the peak of the galaxy number density, and the X-ray brightness maximum all point to Holmberg 15A occupying the region where the gravitational potential of Abel 85 reaches its minimum. In addition, measurements of its line-of-sight velocity relative to the average motion of the cluster show that Holmberg 15A moves more slowly than most other members, which is expected if it resides close to the dynamical center of the system. Over billions of years' dynamical friction, the gradual drag that a massive galaxy experiences as it moves through a sea of smaller galaxies and dark matter particles causes the most massive systems to lose orbital energy and sink toward the center. As this process operates, smaller galaxies spiral inward and may eventually merge with the central galaxy, adding their stars and dark matter to its outer layers. In this way, Holmberg 15A has grown within Abel 85 by accreting companions that fall into the central region of the cluster. The evidence for this growth is written in the extended diffuse envelope of starlight that surrounds the bright core of the galaxy, blending gradually into the faint intracluster light that pervades the central region. Deep imaging shows that the brightness of Holmberg 15 does not drop off sharply at a particular radius. Instead, its light profile extends to large distances where individual stars are no longer resolved and their combined glow forms a smooth background. This extended halo reflects the accumulated contributions of many disrupted satellites and stripped stars, whose orbits have been altered by repeated interactions in the dense central environment. Around Holmberg 15, smaller galaxies continue to orbit within the central region, some of them already showing signs of tidal disturbance such as asymmetries, elongated shapes or faint streams of stars that bridge the space between them and their massive neighbor. These features indicate ongoing gravitational interactions which transfer energy and angular momentum between the galaxies and feed more material into the central system over time. The hot intracluster gas also responds to the presence of the central galaxy. Near Holmberg 15A, the gas density is higher and the cooling time, the time required for the gas to radiate away its thermal energy, can be shorter than in the outskirts. This can lead to the development of a cooling core, a central region where gas gradually loses energy and would tend to drift inward if no other processes counteract the cooling. In many clusters, and likely in Abell 85 as well, energy input from central activity associated with the dominant galaxy helps to balance this cooling, inflating cavities or bubbles in the gas and stirring it gently. Observationally, such features appear as subtle depressions in X-ray brightness near the cluster center, often roughly aligned with radio emission from extended structures associated with the central galaxy. These details reveal a close coupling between Holmberg 15A and the surrounding intracluster medium, in which the galaxy does not simply sit passively at the center, but participates actively in the energy balance of the gas. On slightly larger scales, gravitational lensing studies and dynamical modeling of galaxy motions show that the dark matter halo of Abell 85 is also centrally concentrated around Holmberg 15A. The galaxy therefore occupies a region where stars' gas and dark matter are all most densely packed. For an observer imagining a slow journey through the cluster, the path inward from the outskirts would reveal an increasing density of galaxies, a strengthening X-ray glow from the hot gas, and a gradual transition toward a central zone dominated by the luminous bulk of Holmberg 15A and its diffuse halo. At intermediate radii, the galaxy distribution still includes many spirals and less massive ellipticals, but as the path approaches the center, the mix becomes more weighted toward large, smooth ellipticals and lenticular systems, reflecting the transformation of galaxies in the dense environment. The central few hundreds of thousands of light-years are thus marked by the presence of Holmberg 15A as a dominant elliptical surrounded by a swarm of smaller companions and embedded in the densest parts of the intracluster medium and dark matter halo. Within this region, the gravitational field is strong enough that the orbits of nearby galaxies and of stars in the extended halo are tightly bound to the central mass concentration. The gradual accretion of satellites and the stripping of their stars continue to add to the diffuse light and to the outskirts of Holmberg 15A, while the overall cluster structure remains centered on this luminous anchor. The galaxy's position, its relatively low peculiar velocity with respect to the cluster, mean its extended stellar envelope, and its coincidence with the peak of the X-ray emitting gas, all support its identification as the central galaxy of Abell 85, marking the location where the cluster's gravitational potential reaches its deepest point, and where the combined effects of long-term dynamical evolution are most clearly expressed in the distribution of matter and light. Holmberg 15 presents itself in visible light as a giant elliptical galaxy, a smooth and rounded mass of stars without the spiral arms, dust lanes, or sharply defined disk that mark many other galaxy types. Its light distribution is dominated by a central glow that gradually tapers outward, and the overall impression in deep images is of a luminous, nearly featureless body surrounded by an extended faint envelope. In standard galaxy classification schemes, such a system falls into the category of an elliptical, meaning that its stars follow largely random orbits, rather than being confined to a thin rotating disk. The shape of Holmberg 15A on the sky appears slightly elongated rather than perfectly circular, indicating that the underlying stellar distribution is not a perfect sphere, but an ellipsoid whose apparent flattening depends on viewing angle. Within this broad form, however, the surface brightness profile, which maps how the intensity of light changes with distance from the centre, follows a smooth trend rather than showing abrupt transitions or prominent substructures. If one imagines tracing the brightness along a line from the centre outward, the intensity drops steadily at first quickly, and then more gradually, and this behaviour can be described with empirical functions that astronomers use to characterise elliptical galaxies. The sheer size of Holmberg 15 sets it apart from normal ellipticals found in less dense environments. Its stellar body extends across distances of many hundreds of thousands of light-years, far larger than the visible extents of typical galaxies such as the Milky Way, and when the diffuse outer envelope is included, its influence in starlight reaches even farther into the surrounding intracluster space. Integrated over this whole volume, the total starlight corresponds to a stellar mass that is among the highest known for galaxies, reflecting its special role as the central system in a rich cluster. The stars that contribute to this light are mostly older, lower mass stars that shine with a relatively steady reddish or yellowish hue, giving the galaxy an overall red colour index compared to younger, more actively star-forming systems. This colour is a direct consequence of the galaxy's star formation history. Observations of its spectrum, which breaks the starlight into individual wavelengths, reveal absorption features typical of an evolved stellar population, with strong lines from elements such as magnesium and iron and relatively weak indicators of young hot stars. These spectral signatures suggest that the bulk of star formation in Holmberg 15A took place long ago, likely when the universe was denser, and mergers and gas accretion were more common, and that in the present epoch its rate of forming new stars is low. Consistent with this, there is little evidence for the large reservoirs of cold gas and dust that would be required to sustain vigorous star formation today. In images taken at wavelengths, sensitive to cool dust or molecular gas, Holmberg 15 appears relatively faint, and radio observations that probe neutral hydrogen also indicate that the central galaxy of Abell 85 is largely depleted of the raw material needed to make many new stars. Kinematically, the stars in Holmberg 15A move in a way that matches its classification as a massive elliptical. Instead of all stars rotating coherently around a single axis as in a disk, their orbits are oriented in many directions, leading to a velocity field dominated by random motions. Spectroscopic measurements across the face of the galaxy show a broadening of stellar absorption lines, which reflects a range of velocities in the line of sight at each position. The width of these lines increases toward the centre, indicating that the typical speed of stars relative to the galaxy's centre of mass is higher there, while in the outer regions the velocity dispersion declines more gradually. This pattern of velocity dispersion, combined with the surface brightness profile, enables astronomers to model the galaxy's mass distribution, including contributions from stars and dark matter. The results show that the total mass enclosed within a given radius rises steeply near the centre and continues to grow out into the extended halo, consistent with a system that sits at the bottom of the cluster's overall dark matter potential. When viewed at higher resolution, the central parts of Holmberg 15A still lack the complex features seen in many disk galaxies. There are no long, thin spiral arms winding toward the centre, no sharply defined central bar slicing across the inner region, and only minimal patchy structure that would indicate clusters of recent star formation. Instead, the central light appears relatively smooth, with gentle variations in brightness that can often be attributed to the combined effects of random stellar clustering and the superposition of unresolved stars along the line of sight. At larger radii, the outer isophotes, the contours of equal brightness become more irregular and may show subtle asymmetries or faint extensions. These irregularities reflect the history of galaxy interactions and mergers that have built up Holmberg 15A over cosmic time. Tidal encounters with other galaxies can pull out streams of stars that later fade into the background, while complete mergers between sizable systems can introduce shells, ripples, or low-contrast substructures that persist for long times. Deep imaging designed to reach very low surface brightness levels sometimes reveals such features as extremely faint arcs or plumes in the outer parts of central cluster galaxies and Holmberg 15. A is no exception. These signatures suggest that the galaxy has grown not only through smooth accretion, but also through discrete events in which entire galaxies have been assimilated. The orientation and ellipticity of Holmberg 15A on the sky can also encode information about its past. Slight twists in the position angle of isophotes with increasing radius may signal that the inner and outer parts of the galaxy are not perfectly aligned, possibly because they formed from mergers with different orbital geometries. Any misalignments between the elongation of the stellar light and that of the surrounding X-ray emitting gas or dark matter potential may further hint at complex assembly processes. However, despite these fine details, the overarching impression in most observations is one of smoothness and regularity. The central galaxy presents a stable luminous mass whose global properties change only slowly over long timescales. Multi-wavelength observations reinforce this picture of an old, massive, relatively quiescent system. In ultraviolet light, which is sensitive to young hot stars, Holmberg 15A is faint compared with galaxies undergoing active star formation, supporting the conclusion that new stars are currently rare. In infrared wavelengths, which can reveal the presence of dust and evolved stars, the emission is dominated by the latter, with only modest signs of warm dust that might be linked to stellar mass loss or weak residual gas heating processes. Together, these data indicate that the galaxy's stellar content is largely in a long-lived evolved phase, with little ongoing transformation of gas into stars. As a brightest cluster galaxy, Holmberg 15 therefore stands as a mature massive elliptical, whose structure and light distribution reflect a long history of growth and interaction within the deep potential well of Able 85. Its smooth stellar body extended envelope red colors and dominance in visible light all mark it as the central stellar concentration of the cluster, while its kinematic properties and multi-wavelength behavior point to a system that has already assembled most of its mass, and now evolves only gradually as it continues to interact with the surrounding galaxies and intra-cluster medium. Far from the bright central glow of Holmberg 15, the galaxy's outer regions extend into a faint diffuse halo of stars that gradually blends into the surrounding light of the Abel 85 cluster. In deep images where long exposures and careful processing reveal structures at very low surface brightness, this outer envelope appears as a soft extended glow that stretches far beyond the radii where ordinary observations might place the visible edge of the galaxy. There is no sharp boundary where the galaxy ends and the cluster begins. Instead, the density of stars declines smoothly with distance from the center, while the contribution from stars that have been stripped from other galaxies and now orbit freely in the cluster gradually becomes more important. The result is a transition zone in which light from Holmberg 15A and light from the intracluster stellar population overlap and merge. Within this halo, individual stars cannot be distinguished at the distance of Able 85, but their combined luminosity fills the outer regions with a very gentle background glow. The stars that make up this extended envelope are mostly older and lower mass, similar in age and composition to the main stellar body of the galaxy, and their distribution is a record of the many interactions and mergers that have contributed to the growth of the central system. Some parts of the halo may contain slightly higher densities of stars forming subtle features such as shell streams or arcs, that stand out only when the image depth is sufficient and the background is carefully subtracted. These structures arise when a smaller galaxy falls into Holmberg 15A on a particular orbit and is gradually torn apart by tidal forces its stars pulled into elongated trajectories that wrap around the larger system. Over time, as the stars continue to move along their paths, these initially sharp features become more diffuse and mixed, eventually blending into the smoother background halo. Even when the original galaxy is no longer recognizable as a separate entity, its former stars continue to orbit within the combined potential of Holmberg 15A and the cluster contributing to the outer light. In some central cluster, galaxies' extremely deep observations reveal an extended coda of light that reaches hundreds of thousands of light-years from the center and Holmberg 15. A appears to share this characteristic of a very large diffuse envelope. The shape of the outer halo can be slightly different from that of the inner galaxy, with isophotes that become more elongated or twisted at greater radii. Such changes in ellipticity and orientation suggest that the outermost stars may have been acquired through interactions along preferred directions, for example along the same filaments of the large-scale structure that feed material into the cluster. Where the diffuse halo is very extended, its light begins to merge into what astronomers call intracluster light, the stellar component that is no longer clearly bound to any one galaxy, but instead orbits in the global potential of the cluster. This intracluster light is thought to originate mainly from stars that have been stripped during past encounters and mergers. Around Holmberg 15, some of this light is closely associated with the galaxy's own envelope, while some stretches farther out, linking the central system to its nearby companions and to the overall cluster environment. In certain regions, faint bridges and plumes may connect Holmberg 15 to neighbouring galaxies, marking paths along which material is still being exchanged. The brightness of the halo decreases steadily with increasing radius, so that beyond some distance the light becomes difficult to distinguish from the background sky. Nevertheless, techniques such as stacking multiple images, careful modelling of the sky, and the use of wide-field detectors have allowed astronomers to trace the envelope of central galaxies like Holmberg 15A to remarkably large scales. Counting discrete traces such as globular clusters or planetary nebulae associated with the outer halo offers another way to probe these regions. These objects, though individually faint at the distance of Hubble 85, can be identified in very sensitive observations and used to map the kinematics and spatial distribution of halo stars. Measurements of their velocities provide information about the mass distribution at large radii, where dark matter and the cluster potential become increasingly important. The motions of these tracers indicate that the gravitational influence of Holmberg 15A and the central region of Hubble 85 reaches far into space, binding not only the bright inner galaxy, but also the extended halo and intracluster stars. Within the halo, the mix of stellar ages and chemical abundances reflects the composite origin of the stars. Some formed in the main body of Holmberg 15A itself, early in its history, while others were born in smaller galaxies that were later accreted. Spectroscopic studies that sample light from different radii often find gradients in metallicity, a measure of the abundance of elements heavier than helium, with higher metallicities nearer the center and more metal-poor populations farther out. This pattern is consistent with a picture in which the central parts of the galaxy, formed from gas that had been enriched by many previous generations of star formation, whereas the outer halo contains a larger fraction of stars from lower mass satellites, which tend to have lower metallicities. Over long timescales, dynamical processes such as phase mixing and violent relaxation act to smooth out irregularities in the stellar distribution, but traces of past events can linger in the outer parts where dynamical times are longer and mixing is less complete. The halo of Holmberg 15. A thus preserves in low contrast patterns of light and subtle kinematic features, a record of the galaxy's growth within the cluster. On the sky, the combined effect of the central galaxy, its extended envelope and the surrounding intracluster light is to create a luminous core to the Able 85 cluster, a region where the background glow of stars never completely fades. Against this backdrop, individual galaxies and compact sources appear superposed on a sea of faint starlight. As one imagines moving slowly inward through these outskirts, the diffuse glow of the halo gradually brightens and becomes more structured, signalling a transition from the outer envelope toward the more concentrated regions of Holmberg 15A, where the stellar density rises and the main body of the galaxy begins to dominate the view. The stars that fill Holmberg 15A form a vast and complex population that carries in their ages and chemical compositions a record of how the galaxy has grown inside the Able 85 cluster. A stellar population is a collection of stars that share similar ages and chemical properties, and in a giant elliptical galaxy like this central system, most of the light comes from old stars that formed billions of years ago. When astronomers take spectra of Holmberg 15, breaking its starlight into many narrow wavelength intervals, they see absorption features characteristic of evolved stars, including prominent lines from elements such as magnesium, calcium, and iron. The overall shape of the spectrum and the strength of these features indicate that the bulk of the stars are relatively old, having formed when the universe was much younger, and that only a small fraction of the light is contributed by very young, massive stars. This conclusion is reinforced by the colors of the galaxy in broad filters. In optical and near-ultraviolet images Holmberg 15, A appears redder than galaxies with active star formation, reflecting the dominance of cooler older stars over hot blue ones. The redness is not due primarily to dust, since there is little evidence for large amounts of dust in the galaxy. Instead, it arises from the intrinsic properties of the stars themselves. The stellar populations also carry clear signatures of chemical enrichment. Chemical enrichment refers to the buildup of elements heavier than hydrogen and helium in successive generations of stars as massive stars fuse lighter elements into heavier ones, and then release them into space when they end their lives in supernova explosions. Over time, this process increases the fraction of heavy elements, often referred to as metals in astronomical language, in the gas from which new stars form. In Holmberg 15, measurements of absorption lines associated with iron and other heavy elements show that the central regions are quite metal-rich, meaning that many cycles of star formation and enrichment took place before most of the present stars formed. In addition, the relative strength of lines from different elements suggests that the enrichment occurred over a relatively short interval in cosmic history, with contributions from massive stars dominating the early chemical evolution. Moving outward from the center, spectroscopic studies reveal gradients in metallicity. The innermost regions tend to have higher metal abundances, while the outer parts show lower values. This pattern matches a picture in which the central body of the galaxy formed from gas that had been heavily enriched by previous generations of stars, while the outer halo includes a larger proportion of stars that originated in lower mass satellites, which generally have lower metallicities. As Holmberg 15 accreted these smaller galaxies through mergers and tidal interactions, their stars were deposited at larger radii, building up a diffuse, somewhat more metal-poor halo around a more metal-rich core. The ages of stars also change with radius, though the variations are subtle. In many brightest cluster galaxies, including Holmberg 15A, the central regions often appear slightly older on average than some parts of the outer halo, consistent with an early intense phase of star formation that built the inner body, followed by a more extended period in which additional stars were added through mergers. The absence of strong emission lines from ionized gas in the spectrum indicates that current star formation activity is low. There is little cold gas available to collapse into new stars, and the hot intracluster medium combined with the energy input from past and present central activity limits the ability of gas to cool and collect in the galaxy's potential well. As a result, the stellar population is dominated by long-lived low-mass stars that evolve slowly and give the galaxy a steady, relatively unchanging glow over long timescales. The history of star formation in Holmberg 15A is also linked to the properties of the intracluster gas. The heavy elements observed in the hot plasma between galaxies must have originated in stars, and a significant fraction of this enrichment is thought to come from massive galaxies like the Central System. Over billions of years, supernovae and stellar winds drive enriched gas out of galaxies and into the wider cluster environment, where it mixes with the ambient medium. The high metallicity of the intracluster gas in Able 85 implies that stars in Holmberg 15A and its companions have processed large amounts of material. This exchange of matter between galaxies and the intracluster medium connects the stellar populations of Holmberg 15A to the larger ecosystem of the cluster. Another important tracer of the galaxy's history is its population of globular clusters, which are dense, roughly spherical groups of stars bound together by gravity. Although individual clusters are too faint to dominate the galaxy's light, their numbers and distribution provide clues to past events. Brightest cluster galaxies often host very rich systems of globular clusters, with tens of thousands of such objects extending far into the halo. Many of these clusters can be divided into subpopulations based on their colors, with one group being more metal-poor and another more metal-rich. In Holmberg 15A, as in similar systems, the more metal-rich clusters tend to be more centrally concentrated and share properties with the stars in the inner galaxy, while the more metal-poor clusters are spread over larger radii, more closely following the extended halo and intracluster light. This arrangement supports a scenario in which the inner metal-rich stellar component formed early and in a deep potential well, while the outer metal-poor stars and clusters were added later through the accretion of smaller systems. Kinematic measurements of stars and globular clusters further illuminate the galaxy's assembly. In the inner regions, the stellar velocity dispersion is high, reflecting the strong gravitational field and the predominance of random motions. As one moves outward, the velocity dispersion may decline, then flatten or even rise again where the cluster potential becomes dominant. The degree of ordered rotation is generally modest, indicating that Holmberg 15A is supported mainly by random motions rather than by rotation. The orbits of halo stars and clusters can be more radial or more tangential, depending on how they were deposited. Systems formed through the gradual accretion of many small satellites often show a mix of orbital types, while major mergers between roughly equal mass galaxies can imprint different signatures on the kinematics. In Holmberg 15A, the detailed orbital distribution encodes the cumulative effects of many such events, though at the distance of Able 85 the data are still limited and some aspects remain uncertain. Despite these uncertainties, the broad picture is that of an early intense episode of star formation and assembly that created a massive metal-rich central body, followed by ongoing growth through the assimilation of smaller galaxies that built up the outer halo and intracluster light. Throughout this history, feedback processes from supernovae and central activity have helped to regulate star formation and to move enriched gas into the wider environment. The present stellar populations, old and relatively quiescent, now evolve slowly, their main changes being the steady aging of stars and the gentle fading of light as the most massive remaining stars complete their evolution. Across the volume of Holmberg 15A, from its bright inner regions to its diffuse outer envelope, the arrangement of stars in age, metallicity and orbital properties summarizes this lengthy history of formation and growth inside a dense cluster. Imagining a path that moves inward through the galaxy, the observer would encounter an increasing concentration of stars, higher typical metallicities, and stronger random motions, all characteristic of a central region that formed early and now dominates the luminous mass at the heart of the system. Moving inward from the extended halo and main stellar body of Holmberg 15, the light distribution begins to change in a way that sets this galaxy apart from many more ordinary ellipticals. At large radii, the surface brightness falls smoothly, following a steep decline with distance from the center. But as the line of sight approaches the innermost regions, the profile does not continue to rise as steeply as one might expect when extrapolating from the outer trend. Instead, the central light flattens into a broad, gently sloping plateau. This flattened inner region is described as a core zone, in which the density of starlight is lower than would be predicted if the outer brightness profile simply continued inward without alteration. In many elliptical galaxies, high-resolution imaging reveals either a steep central cusp, where the surface brightness rises more sharply toward the center, or a modest core with a relatively small radius. Holmberg 15A, however, shows an unusually large core extending over distances of many thousands of light-years, much larger than the central flattening seen in more typical systems. When astronomers fit mathematical functions to the surface brightness profile, they find that a single smooth curve cannot accurately describe both the outer envelope and the inner region. Instead, a change in slope is needed, with one set of parameters for the steep outer profile and another for the shallower central part. The radius at which this change occurs provides a measure of the core size, and in Holmberg 15A, this break radius is particularly large when compared to the effective radius of the galaxy, the scale that encompasses about half of its total light. This disproportionate central flattening suggests that the inner region has been altered by processes that preferentially removed or redistributed stars from the very center. Observationally, the core appears as a nearly smooth low-gradient zone in the brightness maps, with no dramatic peaks or sharp nuclear features at the smallest resolved scales. In some galaxies, compact nuclear star clusters or bright central point sources dominate the very innermost light. But in Holmberg 15A, such components are either absent or very weak compared with the overall stellar body. The innermost isophotes remain roughly elliptical, with only mild deviations from perfect symmetry, implying that whatever processes shaped the core operated in a fairly global manner rather than leaving behind strongly lopsided structures. The stellar colors in the core are similar to those in the surrounding inner galaxy, reinforcing the impression that the stars there are predominantly old and metal-rich. This similarity in color suggests that the core is not simply filled with a different younger population of stars that might have formed from newly accreted gas, but instead represents a region where the density of the same underlying population has been reduced. To probe these central regions, astronomers rely on observations from large ground-based telescopes, equipped with adaptive optics, and from space-based observatories that provide high angular resolution. These instruments can map the inner light profile on scales of a few tens to a few hundreds of light-years, at the distance of Arbel 85, resolving the structure of the core and tracking how the brightness changes with radius. When such data are combined with wider field images that capture the outer body and halo, a complete picture emerges of a galaxy whose light profile is steep and extended at large radii, but remarkably shallow and broad in the center. The existence of a large core in a brightest cluster galaxy like Holmberg 15A is often linked to its assembly history. During major mergers between massive galaxies, stars on low angular momentum orbits can be scattered outward, and the central density profile can be reshaped. Repeated mergers, especially in a dense cluster environment where many massive galaxies interact over long timescales, can magnify this effect, gradually building a central region where the number of stars per unit volume is lower than a simple inward extrapolation would imply. The resulting core is not empty. It still contains many stars, but their distribution is less sharply peaked than in galaxies whose inner regions have experienced fewer such events. In the case of Holmberg 15, the combination of its extended outer envelope-rich merger history inferred from its halo and the unusually broad central flattening all fit together into a picture where dynamical processes have played a strong role in reshaping the innermost stellar distribution. Kinematic measurements support this view by showing that the stellar velocity dispersion remains high throughout the core, indicating a deep gravitational potential, even though the surface brightness rises only slowly toward the center. This means that the mass density does not drop as dramatically as the light might suggest, and that a significant amount of mass is still concentrated in the inner region, but distributed in a way that yields a relatively flat projected light profile. From the standpoint of someone imagining a gradual inward journey crossing the boundary between the main body and the core, would not involve encountering a new visible structure or a sudden change in the appearance of the stars. Instead, the transition would be experienced as a subtle shift in how rapidly the brightness increases as the line of sight approaches the center. The star field would remain crowded, yet the rate at which the stellar density builds up would be less steep than expected, as if the central region had been gently carved out over time by the cumulative effects of many dynamical interactions. The scale of this core spanning many thousands of light-years means that it encompasses a substantial volume of the galaxy within which the balance of light and mass reflects past events that have altered stellar orbits and redistributed stars. At the outer edge of the core, stars still follow a range of orbits typical of an inner elliptical galaxy, but as the path continues inward, the phase space of orbits becomes increasingly influenced by the global potential, shaped by both the stellar mass and additional unseen mass components. The core of Holmberg 15 thus represents a distinct structural component within the galaxy, separating the bright, more steeply declining outer profile from the inner zone, where the central light is strikingly shallow. As the exploration moves deeper into this region, the emphasis shifts from describing the overall form of the galaxy to understanding how the detailed structure of the core encodes information about missing light-altered stellar distributions and the gravitational landscape that governs the motions of stars in the central tens of thousands of light-years. In the inner regions of Holmberg 15A, where the light profile flattens into the broad core described before, careful analysis reveals that not only is the central brightness shallower than expected, but a substantial amount of starlight appears to be missing when compared with the simple inward continuation of the outer profile. Astronomers begin by fitting the surface brightness of the galaxy at large radii with an empirical function that describes how elliptical galaxies usually behave, then extend this function inward to predict how bright the center would be if no additional processes had altered it. For many massive ellipticals, the observed inner light falls somewhat below this extrapolated curve, indicating the presence of a core. In Holmberg 15A, the difference between the predicted and observed central light is especially large. This difference is often called a light deficit, and when converted into mass using reasonable estimates of how much light each star contributes, it becomes a mass deficit, a measure of how many stars are absent from the central region relative to the outer structure. In this galaxy, the inferred mass deficit corresponds to many billions of times the mass of the Sun, in stars spread over a volume that spans many thousands of light years. Instead of a steep and sharply rising central cusp, the inner profile levels off into a luminous plateau whose brightness changes only slowly with distance from the center. This plateau is still bright in absolute terms because the galaxy as a whole is very luminous, but its shape signals that the central stellar density has been reduced compared with what would be expected in the absence of such a core. The stars that remain in this region are arranged in a way that preserves overall smoothness and symmetry, yet detailed maps show gentle variations and low-level asymmetries that hint at a complex dynamical past. By examining isophotes, the contours of equal brightness across the core, astronomers find that their shapes and orientations change only gradually with radius. The ellipticity may increase or decrease slightly, and the position angle may twist by a modest amount, but there are no sudden distortions that would indicate a recent highly disruptive event. This smoothness suggests that whatever processes created the core operated over timescales long enough for the stellar distribution to relax into a relatively stable configuration. At the same time, the very size of the core implies that these processes involve the redistribution of a large number of stars, not just minor rearrangements in a small central zone. Dynamical models offer a way to connect the observed structure of the core with the underlying gravitational field. By combining the surface brightness profile with measurements of stellar velocities, astronomers can infer how mass is distributed in 3 dimensions, in Holmberg 15. Such models indicate that the total mass density in the core, including both stars and any additional unseen components, still rises toward the center, even though the projected light profile flattens. This means that stars have been moved outward or onto different orbits in a way that lowers the surface brightness while leaving a deep gravitational well in place. The central regions remain dominated by random stellar motions at high speeds, indicating that strong gravitational forces are present. The apparent mismatch between light and gravitational strength in the core, where the potential is deep but the surface brightness is comparatively low, is a key feature of this depleted structure. To quantify the degree of depletion, astronomers compare Holmberg 15A with samples of other core galaxies, plotting core size and light deficit against global galaxy properties such as total luminosity and velocity dispersion. In many systems, there is a trend in which larger, more luminous galaxies tend to have larger cores and greater light deficits, consistent with more extensive dynamical reshaping in massive systems. Holmberg 15. A lies toward the extreme end of these relations, with a core that is large even by the standards of brightest cluster galaxies. Its break radius, the scale at which the profile changes slope, and its inferred mass deficit stand out when placed alongside measurements from other central galaxies in rich clusters. This suggests that the processes that create and enlarge cores have been particularly efficient in this system. One frequently discussed mechanism involves the action of massive central concentrations that form during mergers between galaxies. When two massive galaxies come together, their central mass concentrations sink toward the common center of the new system through dynamical friction, and as they orbit one another, they can transfer energy to surrounding stars. Stars that pass close to this central region can receive gravitational kicks that send them onto wider orbits, effectively scouring out the center and producing a core. Repeated occurrences of such events, especially in an environment like the Abell 85 cluster, where mergers have been common over cosmic time, can build up a large central region where the stellar density is lower than in systems that have experienced fewer or less violent encounters. In Holmberg 15A, the scale and depth of the core are consistent with a history in which many such interactions have taken place. Although direct evidence for individual past mergers can be subtle or erased by relaxation over long timescales, the combined outcome remains imprinted in the global structure of the core and halo. Another way to probe the distribution of stars in the core is to look at its response to the surrounding environment. For example, the presence of faint stellar streams or shells just outside the core can signal that material from disrupted satellites has been added to the inner galaxy. In deep images, Holmberg 15 shows low contrast features in its inner halo that may represent the remnants of such accretion events. These features tend to be aligned in particular directions, perhaps reflecting preferred infall paths along large-scale filaments or past group mergers. Inside the core itself, however, the light distribution is remarkably free of distinct substructures, suggesting that the stars there have been well mixed by the central potential. Numerical simulations of galaxy formation and clusters support the idea that repeated mergers and dynamical interactions can produce large cores and extended halos similar to those observed in systems like Holmberg 15A. These simulations follow the orbits of stars and dark matter under gravity, showing how central densities can be reduced as stars are ejected from the innermost region or moved to larger radii. While details of individual histories vary, a common outcome is that the most massive galaxies and cluster centers develop flattened inner profiles and significant mass deficits. In this context, the core of Holmberg 15A can be seen as a natural though extreme example of this broader class of central galaxies. The precise amount of missing light and the exact shape of the core depend on choices made in fitting profiles and converting light to mass, so there are uncertainties in the derived numbers. Yet across different modelling approaches, the conclusion remains that the central stellar density has been strongly modified. As the inward exploration continues through the core, the combination of a shallow light profile high stellar velocity dispersion and evidence for a deep gravitational well all point to a central region where the visible stars represent only a portion of the total mass, and where past dynamical reshaping has left a distinctive signature in the structure of the galaxy's inner tens of thousands of light years, deep inside the broad core of Holmberg 15. The visible stars become more than a source of light. They act as traces of the gravitational field that shapes their orbits. In a galaxy, gravity determines how fast stars move and how their paths curve through space, so measuring stellar motions offers a way to infer how mass is distributed, including any components that do not shine. In Holmberg 15A, where the central light profile is unusually flat, yet the overall system is extremely massive, this dynamical information is especially important. Observers begin by collecting spectra at many positions across the face of the galaxy, using long slits or integral field units that break up the central region into a mosaic of small spatial elements. In each element, the combined light of countless stars forms absorption lines at characteristic wavelengths that depend on the elements present in their atmospheres, When these stars move along the line of sight, their motion slightly shifts the positions of the lines through the Doppler effect. If many stars in a given region share similar velocities, the lines appear relatively narrow and well-defined. If their velocities span a wide range, the lines broaden and their shapes become more complex. By analysing these shifts and broadenings, astronomers can determine both the average motion and the spread of velocities at each location. The spread is called the velocity dispersion, and in a system dominated by random stellar motions, it is a key measure of how tightly stars are bound by gravity. In the core of Holmberg 15A, the velocity dispersion is high, reaching values of several hundreds of kilometers per second near the center. This means that stars there move rapidly along the line of sight, both toward and away from the observer, in many different directions within the galaxy's three-dimensional potential. As one moves outward from the center along the core, the dispersion remains large, then gradually declines at larger radii, reflecting the combined influence of the galaxy's stellar mass and the larger-scale dark matter and cluster potential. At the same time, measurements of the mean velocity as a function of position reveal only modest rotation. Unlike a disk galaxy where stars orbit coherently around a central axis, Holmberg 15A shows only gentle large-scale gradients in mean velocity, indicating that rotation plays a secondary role in supporting the galaxy against gravity. Instead, random motions dominate, and the gravitational field must be strong enough to confine stars moving at such high speeds. The pattern of velocity dispersion across the core carries information about how mass is concentrated. If mass was spread out more evenly, stars would not need to move as quickly to remain bound, and the central dispersion would be lower. The observed high central dispersion combined with the relatively low central surface brightness suggests that the mass density rises more steeply than the light would imply. To translate these observables into a three-dimensional mass distribution, astronomers construct dynamical models that link the light-profile stellar orbits and gravitational potential. One simple class of models assumes that stars move in a smooth static potential, and that their velocities follow certain statistical patterns, such as being isotropic, meaning that motions are equally likely in all directions. More sophisticated models relax these assumptions and allow for anisotropy, in which orbits can be more radial or more tangential, and for variations in orbital structure with radius. In the case of Holmberg 15A, the broad core and extended envelope require models that take into account both the dense inner regions and the influence of the cluster environment at larger scales. The process begins by converting the observed surface brightness profile into a three-dimensional light density under the assumption of a particular geometric shape, such as an oblate or triaxial ellipsoid. A mass-to-light ratio, which specifies how much mass is associated with each unit of starlight, is then applied to estimate the stellar mass distribution. Dark matter is included as an additional, more extended component whose contribution grows with radius. With these ingredients, a trial gravitational potential is constructed. The next step is to populate this potential with a representative library of stellar orbits. In orbit superposition methods, many possible orbits are calculated that sample a wide range of shapes and energies, from nearly circular paths to highly elongated trajectories that plunge close to the center and then swing out to larger radii. Each orbit contributes light and kinematic signatures to different regions of the model galaxy. By adjusting the weights assigned to each orbit, astronomers seek a combination that reproduces both the observed surface brightness and the measured velocity dispersion and higher order line profile shapes at all positions. If the model underestimates the central velocity dispersion, more tightly bound orbits or additional mass in the central regions are introduced. If it overestimates the dispersion, the central mass or the concentration of radial orbits is reduced. In Holmberg 15. This modelling exercise shows that the observed high central velocity dispersion requires a deep gravitational potential in the core deeper than would be produced by the stellar mass alone if it followed the observed light profile with a constant mass-to-light ratio. Variations in orbital anisotropy can shift some of the burden, because stars on more radial orbits can produce higher dispersions without as much central mass, while stars on more tangential orbits tend to reduce the line-of-sight dispersion. However, within reasonable ranges of anisotropy consistent with the shapes of spectral lines and the overall structure of the galaxy, a substantial excess of central mass remains necessary to match the data. This excess mass does not show up directly in the light distribution, which stays relatively flat in the core, so it must be either dark or concentrated in a way that does not significantly alter the surface brightness profile. The integrated effect of this inner concentration is to raise the speeds of stars within a certain radius, imprinting a strong central peak in the velocity dispersion profile, even though the visible stellar density does not rise steeply. In addition to the mean dispersion, subtle deviations from a perfect Gaussian line profile provide further clues. When the velocity distribution is symmetric and dominated by random motions, the absorption lines have a characteristic shape that can be described by a Gaussian curve. If there is a surplus of high-velocity stars in the wings of the distribution, or if streaming motions contribute, the lines become skewed or more peaked, and these changes are captured by higher-order parameters in the line profile analysis. In Holmberg 15A, the central line shapes suggest a mix of orbits and a significant share of stars moving on paths that take them through the inner potential well at high speeds. Dynamical models that include these higher-order constraints reinforce the need for strong central gravity. The uncertainties in these interpretations arise from several sources. The exact shape and orientation of the galaxy in 3 dimensions are not directly observed, so assumptions about symmetry can influence the inferred mass distribution. The mass-to-light ratio of the stellar population may vary with radius, if there are gradients in age or metallicity, and such variations can affect how much mass is assigned to the visible stars. The nature and distribution of dark matter in the inner regions also introduce uncertainties, since dark matter is usually expected to be less centrally concentrated than the stars. Yet in some models it can contribute non-negligibly, even at small radii. Despite these complexities, a consistent picture emerges in which the observed stellar motions in the core of Holmberg 15 demand a central concentration of mass that greatly deepens the potential well over a region spanning many thousands of light years. The stars moving rapidly on orbits shaped by this potential map out its depth and shape through their velocities, providing the main empirical basis for estimates of how much mass is enclosed within the inner core and over what radius its influence dominates the dynamics of the visible stellar population. The high stellar velocities observed in the core of Holmberg 15A invite a more quantitative step in the analysis in which the central mass concentration is not only recognized but weighed as carefully as possible. The guiding idea is simple. Stars move under gravity, and the stronger the gravity in a given region, the higher the speeds needed for stars to remain bound. In practice, extracting a reliable mass from this principle in such a distant and complex system requires detailed modelling and careful treatment of uncertainties. The starting point is the combination of the surface brightness profile, which traces how starlight is distributed on the sky, and the maps of velocity dispersion and higher order line profile shapes across the core. From these observables, astronomers construct families of dynamical models, each of which specifies how much mass is present in stars in dark matter and in any additional central component that does not follow the light. The central question is how large this extra component must be to reproduce the observed kinematics while remaining consistent with the light distribution. In these models, the stellar mass is tied to the light by a mass-to-light ratio that may be fixed or allowed to vary slowly with radius reflecting the known gradients in stellar populations. Dark matter is included as a smoothly varying halo, often parameterized by functions that are motivated by numerical simulations of structure formation. These two components together set a baseline gravitational potential. When the model contains only stars and dark matter, without an additional central mass, the predicted velocity dispersion in the innermost regions of Holmberg 15A falls short of the measured values. The stars in such a model do not move fast enough to match the broad absorption lines seen in the spectra. Adding more dark matter concentrated at small radii does not fully solve this because dark matter halos in most formation models do not naturally gather enough mass into the very center without conflicting with other constraints. To raise the central velocity dispersion to the observed levels while keeping the surface brightness profile and outer kinematics intact, the models introduce a compact centrally located mass component whose gravitational influence is strongest within a radius of a few thousand light-years. This component is interpreted as a supermassive black hole, a region in which matter is confined within an event horizon from which light cannot escape. In the dynamical models, the black hole is represented simply as a point mass at the center, and its value is adjusted until the predicted velocity dispersion profile matches the observed one as closely as possible. When this is done for Holmberg 15. Using high-resolution kinematic data, the inferred mass of the central object lies in the range of tens of billions of times the mass of the Sun, making it one of the most massive black holes directly estimated through stellar dynamics. The exact value depends on the details of the modelling, including the assumed geometry, the orbital anisotropy, and the adopted stellar mass-to-light ratio. Some models yield a mass closer to about 20 billion solar masses, while others favour values nearer 40 billion solar masses. Even at the lower end of this range, the black hole is extremely massive compared with the central objects in most galaxies, which more typically have masses of millions to a few billions of solar masses. Despite these impressive numbers, significant uncertainties remain. One source of uncertainty arises from the limited spatial resolution of the observations. The region where the black hole exerts its strongest influence on stellar motions, sometimes described as its characteristic inner zone, is small compared with the distance to Abel 85. Even with large telescopes and adaptive optics, the innermost light is blurred by the point spread function of the instrument and atmosphere. Imperfect knowledge of this blurring can affect the inferred steepness of the central velocity dispersion peak, and as a result the derived black hole mass. Another uncertainty comes from the orbital structure of the stars. If stellar orbits are more radial in the center than assumed in a given model, stars can reach high line-of-sight speeds without requiring as much central mass, while more tangential orbits would have the opposite effect. Constraining this anisotropy requires not only the velocity dispersion, but also higher-order moments of the line-of-sight velocity distribution, which are more difficult to measure accurately at large distances. Different modelling approaches, such as orbit superposition methods versus simpler genes models, treat anisotropy in different ways and can arrive at somewhat different mass estimates even when applied to the same data. The stellar mass-to-light ratio also plays a role. If the central stellar population has a higher mass-to-light ratio than assumed, perhaps due to a different mix of low-mass stars, then stars alone may contribute more to the gravitational potential, leaving less mass to be assigned the black hole. Conversely, if the stellar mass-to-light ratio is lower, the required black hole mass increases. Observations of stellar populations through spectral features provide some constraints, but degeneracies between age metallicity and the distribution of stellar masses leave room for variation. The shape and concentration of the inner dark matter halo add another layer of complexity. In many galaxies, dark matter contributes relatively little to the mass budget inside the effective radius, but in a brightest cluster galaxy like Holmberg 15A, the cluster environment can alter this balance, and some dark matter may be present even at small radii. Including a more concentrated dark halo can reduce, though not eliminate, the need for an extremely massive black hole. Because of these intertwined factors, the quoted black hole mass for Holmberg 15A is usually accompanied by sizable error bars and explicit statements about the assumptions that underlie it. Nonetheless, across a range of plausible models, the mass consistently emerges as being of order tens of billions of solar masses. Tests in which the central mass is set to much smaller values fail to reproduce the observed central velocity dispersion and line profile shapes even when anisotropy and halo structure are varied within reasonable limits. On the other hand, models with even larger black hole masses than the favoured values tend to overshoot the observed dispersion or produce kinematic features that are not seen. The best-fitting solutions occupy a relatively narrow band in this parameter space, all pointing to an extremely massive central object. Comparisons with other galaxies where black hole masses have been measured through similar dynamical techniques show that Holmberg 15A lies near the upper extreme of the observed distribution. A few other galaxies and cluster centers host black holes with masses approaching or slightly exceeding 10 billion solar masses, but the value inferred for Holmberg 15A is larger still in many analyses. This does not mean that it is uniquely special in the universe, since current surveys are incomplete, and very massive black holes may be difficult to detect, but it does indicate that this central object belongs to the most massive class known through direct dynamical measurements. The modelling also yields an estimate of the radius within which the black hole's gravity becomes the dominant contribution to the stellar motions, though the detailed exploration of that innermost domain rests on both the mass inferred here and on higher resolution observations. For the present purpose, the key outcome is that the shallow, central light profile combined with strong stellar motions requires a compact concentration of mass whose best estimate lies in the tens of billions of solar masses range. Within this framework, Holmberg 15A is regarded as hosting an unusually massive supermassive black hole, whose presence is revealed not by direct imaging of the event horizon, but by the collective motion of the stars that orbit within its deep gravitational well. In many galaxies studied over the past decades, the mass of the central black hole does not appear to be an entirely independent quantity, but is instead correlated with properties of the surrounding stellar system. These empirical connections, often called scaling relations, link the black hole mass to measures such as the stellar velocity dispersion in the bulge, the total stellar mass or luminosity of the spheroidal component, and in some cases the structure of the central light profile. A scaling relation is simply a trend in which one property tends to increase or decrease in a regular way, with another with some scatter around the general pattern. For ordinary massive ellipticals and bulges, the most widely used relations indicate that black hole mass grows roughly in step with the depth of the local gravitational potential traced by the stellar velocity dispersion and with the total mass of the stars in the central regions. When these relations are plotted on logarithmic axes, Most galaxies occupy a relatively narrow band, although individual systems can lie above or below the mean trend. In the regime of very massive galaxies, particularly brightest cluster galaxies, the situation becomes less clear because there are fewer systems with reliably measured black hole masses, and uncertainties increase. Holmberg 15. A sits in this sparsely populated high-mass region, and provides an important test of how far the usual relations extend. Its central stellar velocity dispersion averaged over the inner regions outside the very core is high, reflecting the strong gravitational field of a massive galaxy embedded in a cluster center. If one uses the standard relation between black hole mass and velocity dispersion derived from samples of less massive galaxies, this dispersion would predict a central object of the order of a few billions of solar masses, similarly using the relation between black hole mass and bulge stellar mass, and adopting estimates of the stellar mass of Holmberg 15A based on its total luminosity and mass-to-light ratio would yield a characteristic expected mass, also in the range of a few billions to perhaps around 10 billion solar masses, with uncertainties arising from the details of the stellar population. However, the dynamical modelling described earlier, which fits the observed stellar velocities in the core points to a central mass in the range of tens of billions of solar masses. This inferred value lies significantly above the mass that would be predicted by simply extrapolating the standard relations. On a plot of black hole mass versus velocity dispersion, Holmberg 15A appears displaced upward toward higher mass at roughly the same dispersion. On a plot of black hole mass versus bulge stellar mass, it likewise occupies a region where the central object is unusually heavy compared with the stellar content. The degree of this offset depends on the precise black hole mass adopted and on the specific form of the scaling relation chosen, but in many analyses Holmberg 15A ranks among the strongest positive outliers known. It is important to recognize that these comparisons are subject to limitations. The original scaling relations are anchored by samples of galaxies where black hole masses have been measured through stellar dynamics, gas kinematics, or reverberation mapping in active nuclei, and those samples contain relatively few brightest cluster galaxies with extremely high stellar masses and large cores. As a result, the relations are best constrained in the intermediate mass regime and become less certain when extrapolated to the highest masses. The intrinsic scatter, a measure of how widely individual galaxies deviate from the mean trend, also appears to increase at the top end, so the presence of some outliers is expected. In addition, the velocity dispersion used in the relations is often measured within a standard aperture or effective radius, and in central cluster galaxies like Holmberg 15A, the dispersion profile can be influenced by the surrounding cluster potential as well as by the galaxy itself. Differences in measurement techniques and apertures can shift a galaxy's position slightly on the diagram. Nevertheless, even when these factors are taken into account, the mass inferred for the central object in Holmberg 15A remains high compared with the typical expectations from the standard trends. There is another related connection that involves the size of the galaxy's central core and the mass of its black hole. In many core elliptical galaxies, larger cores tend to be associated with more massive central objects, consistent with the idea that dynamical processes linked to black hole growth and mergers help to carve out the core by ejecting or redistributing stars. When the core radius and light deficit of Holmberg 15A are compared with those of other galaxies, its large depleted region aligns qualitatively with a very high black hole mass. In fact, some studies suggest that if one uses the relation between core properties and black hole mass, rather than the velocity dispersion relation Holmberg 15, A appears somewhat less extreme because its core is also exceptionally extended. This does not remove the tension with the more commonly used relations, but it shows that the galaxy's inner structure and central mass are at least broadly consistent with each other in the context of models where cores grow through repeated mergers of central objects. The position of Holmberg 15. A in these various diagrams has implications for how the coevolution of galaxies and black holes is understood. If its mass estimate is accurate within the quoted uncertainties, it suggests that at very high masses the central black hole can grow more rapidly or by different channels than the surrounding stellar component, leading to a steepening or bending of the scaling relations. Alternatively, it could indicate that some systems have experienced histories that place them above the average trend, for example through a sequence of mergers that preferentially increase the black hole mass relative to the stellar content. In either case, such objects highlight the need for caution when extrapolating relations derived from moderate mass galaxies into regimes where few direct measurements exist. At the same time, the existence of galaxies with more modest black holes at similar stellar masses shows that not all massive systems share the same path. Within the observational uncertainties and the limited samples available, Holmberg 15 thus represents an important though not unique data point at the high mass end. Its inferred central mass, coupled with its large core and role as a brightest cluster galaxy, places it near the upper boundary of current empirical distributions. As the inward exploration continues, the focus shifts from how this central mass compares with broader trends to how such a massive object might have formed and grown over cosmic time within the dense environment of Abell 85, and how its gravity shapes the innermost regions, where its influence dominates the motions of surrounding stars and gas. The presence of an extremely massive central object in Holmberg 15A raises the question of how such a black hole can grow to tens of billions of times the mass of the Sun within the lifetime of the universe, and current understanding points to several channels that likely work together over long timescales rather than a single simple route. In broad terms, growth can proceed through the accretion of gas through mergers with other black holes, and through the gradual capture of stars and compact remnants, all operating within the evolving environment of the Abell 85 cluster. In the early universe, when galaxies were younger and gas was more abundant, central black holes are thought to have grown rapidly during active phases in which large amounts of gas flowed toward the center, forming an accretion disk and releasing vast quantities of radiation as the gas lost energy and spiraled inward. Such phases are seen today in quasars and luminous active galactic nuclei, where the light from the central engine can outshine the host galaxy at many wavelengths. For a galaxy that eventually becomes a brightest cluster galaxy, these active periods likely occurred at high redshift when the progenitor systems of Holmberg 15A were still assembling. During these episodes, the black hole mass could increase quickly, especially if accretion proceeded at a significant fraction of the characteristic rate at which radiation pressure balances gravity in a thin disk, allowing exponential growth over timescales of hundreds of millions of years. In addition to smooth gas accretion, mergers between galaxies bring their central black holes together. When two galaxies of comparable mass collide and eventually merge, their central objects sink toward the new common center, under the influence of dynamical friction, forming a bound binary. As this binary hardens, interactions with stars and gas can remove energy and angular momentum from the orbit, gradually shrinking the separation between the two black holes. Stars that pass close to the binary can be slung out to larger radii, or even ejected from the galaxy, a process that both enlarges the central core and helps the binary to coalesce. Eventually, at small separations, gravitational waves carry away the remaining orbital energy, and the two black holes merge into a single, more massive object. In a dense environment like the central region of a cluster where many mergers occur over cosmic time, this process can repeat multiple times, each event stepping the central mass upward. The large core and extended halo of Holmberg 15A, together with its position at the center of Abell 85, are consistent with a history in which many progenitor galaxies have fallen in and merged, each potentially bringing its own central black hole that contributed to the growth of the present object. The cluster environment also influences how gas is supplied to the central regions. In the early phases of cluster assembly, when group-size systems first came together, significant amounts of cold gas could still flow along filaments of the cosmic web into the central galaxies, fueling both star formation and black hole accretion. As the cluster matured and the intracluster medium was heated to high temperatures, the supply of new cold gas dwindled, but cooling of the hot gas in the central regions could still in principle feed the nucleus. Observations of many clusters show that in their cores, the radiative cooling time of the gas can become shorter than the age of the system, leading to what is often called a cooling core. Left unchecked, this cooling would cause gas to condense and flow inward at high rates. However, in many systems, including the central region of Abell 85, there is evidence that energy input from the central galaxy's nucleus helps to offset this cooling. Radio jets, cavities in the X-ray emitting gas, and subtle temperature structures point to a feedback cycle in which gas that cools enough to approach the center feeds the black hole, which in turn releases energy that heats and stirs the surrounding medium, reducing the net inflow. Over long periods, such a feedback loop can maintain a balance between cooling and heating, allowing some growth of the black hole while preventing runaway condensation of gas. In Holmberg 15A, the details of this cycle are not fully constrained, but the presence of a dense intracluster medium, the likelihood of past central activity, and the structure of the cluster core all suggest that similar processes operate. Another slower channel for growth involves the capture and disruption of individual stars and compact objects in the nuclear region. Stars on orbits that bring them very close to the black hole can be tidally disrupted, with some of their material accreted and some ejected. Over billions of years, the cumulative effect of many such events can add mass, though this contribution is generally small compared with that from gas accretion and black hole mergers in the most massive systems. However, in the very center of a galaxy with high stellar density and complex orbital structure, such interactions form part of the ongoing exchange of energy and mass between the stellar component and the central object. The question of how the black hole in Holmberg 15A began its growth touches on the broader issue of black hole seeding in the early universe. Two main paths are often discussed in models. In one, the seeds are the remnants of the first generation of massive stars which leave behind black holes with masses of tens to a few hundreds of solar masses. In the other, black holes form more directly from the collapse of dense gas clouds in early galaxies, producing seeds with masses of tens of thousands to perhaps 100,000 solar masses. Regardless of the precise seeding mechanism, which remains uncertain for any individual system, further growth by accretion and mergers is required to reach the extreme masses seen in brightest cluster galaxies. For Holmberg 15, the specific sequence of events that led from an initial seed to a black hole of tens of billions of solar masses is not directly observable, but simulations of structure formation in a universe with dark matter and dark energy show that central galaxies in massive clusters can, in principle, follow growth histories that assemble such large masses by redshift zero, provided that early accretion is efficient and that mergers between massive galaxies and their central black holes occur repeatedly. The observed combination of a very massive central object, a large depleted core, and a position at the cluster center is broadly consistent with these scenarios, even though details for this specific galaxy remain model-dependent. At late times, the growth rate of the black hole is expected to slow as the supply of cold gas diminishes and the cluster environment becomes more static. The present-day accretion rate may be relatively low, producing only modest nuclear luminosity, while still providing enough energy to interact with the surrounding intracluster medium. In this phase, the black hole can be thought of as a long-lived central mass that has already reached most of its final size, with any ongoing growth representing only a small fraction of its current mass over the remaining lifetime of the cluster. The overall picture that emerges from these lines of evidence and modelling is that the central black hole in Holmberg 15A has grown through a combination of early rapid accretion, successive mergers with other central objects during the assembly of the cluster, and continued, though now more moderate, feeding from the hot gas and surrounding stars. The relative importance of each channel at different times is still a subject of active research, and some details such as the precise seeding process and the exact sequence of past mergers remain uncertain. Even so, the mass inferred from stellar dynamics, the galaxy's structural properties and the nature of its cluster environment together support the view that multiple growth pathways operating over billions of years within a dense and evolving setting have combined to build one of the most massive known central objects in a galaxy today. Within the inner few thousands of light-years of Holmberg 15, the gravitational field changes character as the contribution from the central black hole grows from a subtle influence to the dominant force shaping stellar motions. Astronomers often describe this transition using the idea of a sphere of influence, a region within which the gravitational pull of the black hole is stronger than that of the surrounding stars. In simple terms, the radius of this sphere can be estimated by finding the distance from the center at which the mass of stars enclosed equals the mass of the black hole. Outside this radius, the combined mass of the stellar component and dark matter sets the overall potential, and the black hole acts as a small addition at the center. Inside it, the central object contributes a significant and then increasingly large fraction of the enclosed mass. In Holmberg 15A, where the inferred black hole mass is of the order of tens of billions of times the mass of the Sun, and the stellar density in the core is relatively low. Compared with many other ellipticals, this sphere of influence extends over a radius of many hundreds to a few thousands of light-years. Although this distance is tiny compared with the full extent of the galaxy and the cluster, it still encompasses a volume populated by countless stars whose orbits are shaped primarily by the central point-like mass. Within this inner region, stars move on orbits that respond to a gravitational potential that is nearly Keplerian, meaning that it is dominated by an inverse distance dependence associated with a central mass. In such a regime, the speeds of stars on bound orbits increase as they draw closer to the center, and their orbital periods decrease, with a predictable relation between orbital size and period. However, in a real galaxy, orbits are not simple closed ellipses as in a two-body problem. The presence of residual stellar mass, the overall shape of the potential, and the distribution of angular momenta all contribute to a complex mixture of orbital families. Some stars move on elongated, nearly radial paths that carry them deep into the central regions before flinging them back out to larger radii, while others follow more circular or more inclined trajectories that keep them at intermediate distances. In Holmberg 15A, the depleted core and high-velocity dispersion imply that many stars in the sphere of influence occupy orbits that have been reshaped by past dynamical processes, including interactions with earlier generations of central binaries. The density of stars within the sphere of influence is still high in absolute terms, but because so many stars have been displaced from the innermost volume, the number density rises less steeply toward the center than it would in a galaxy with a sharp central cusp. This means that from the standpoint of the stellar distribution, the core remains relatively shallow, while from the standpoint of gravity the black hole dominates. If one were able to track the motion of individual stars very close to the center, their paths would show the characteristic signatures of motion in a steep, central potential with high speeds and tight curvature. At the distance of Abell 85, such direct tracking is beyond current capabilities, but the integrated light of many stars still encodes the average properties of their orbits. The velocity dispersion peaks within the sphere of influence, reflecting the increased gravitational acceleration, and then declines outward as the influence of the central mass fades relative to that of the extended stellar and dark matter components. The shape of the dispersion profile, especially its inner slope and degree of central enhancement, is a key observable that dynamical models match to infer both the size of the sphere of influence and the mass it encloses. Another way to visualize the inner region is to consider the gravitational potential contours surfaces on which a test particle would have the same potential energy. Far from the center, these contours resemble those produced by an extended, roughly ellipsoidal mass distribution, reflecting the shape of the galaxy and the cluster halo. Closer in within the sphere of influence, the contours become more nearly spherical and centered on the black hole, because the potential from a point-like mass is spherically symmetric. This change in shape affects the variety of stable orbits available. Some orbital families that can exist in a more gently varying potential are disrupted or transformed, while others become more prominent. The net result is a central region where the orbital structure is heavily influenced by the presence of the black hole, even if the surface brightness retains a smooth and featureless appearance. The gas content within the sphere of influence is relatively modest in a system like Holmberg 15A, where cold gas and dust are scarce. However, the hot intracluster medium can in principle penetrate into the central zone, and any cooler gas that manages to condense from it may settle into a rotating disk or filamentary structures that thread the inner region. Observations of some brightest cluster galaxies reveal such structures in ionized or molecular gas, often in the form of narrow filaments or small disks that extend over a few hundreds or thousands of light years. In Holmberg 15, available data suggest that any such features are weak or difficult to detect, consistent with the idea that the present-day accretion rate is relatively low, and that most of the central volume is occupied by stars in random motion and by diffuse hot gas. Nonetheless, the potential presence of small amounts of cooler gas offers a pathway for ongoing, though limited, feeding of the black hole as material loses energy and angular momentum and slowly spirals inward through the sphere of influence. Compact stellar remnants such as white dwarfs, neutron stars, and stellar mass black holes also inhabit this inner region. Over time, processes such as dynamical friction and mass segregation can cause the more massive remnants to sink toward the center, altering the local mass distribution. Encounters among these compact objects and with the central black hole can lead to events in which objects are captured or disrupted, adding to the central mass in small increments. The overall contribution of such processes to the growth of a black hole, as massive as the one in Holmberg 15A, is likely modest compared with earlier episodes of gas accretion and massive black hole mergers, but within the sphere of influence they form part of the ongoing dynamical evolution. Close interactions between stars and the central object can also produce transient phenomena such as tidal disruption flares, in which a star that wanders too close is torn apart with some of its material accreted and some ejected. At the large distance of Abell 85, detecting such rare events in Holmberg 15A would be challenging, but models of the stellar distribution can estimate the rate at which stars are likely to pass within critical distances of the black hole. In a core galaxy with a relatively shallow inner density profile, these rates may be lower than in galaxies with steep cusps because fewer stars occupy very tightly bound orbits. Thus, the structure of the core not only records past dynamical events, but also shapes present-day interactions in the innermost region. From a broader perspective, the sphere of influence in Holmberg 15A defines the region where the black hole's gravitational field directly controls the dynamics of nearby matter. Outside it, the black hole participates in the overall gravitational budget, but does not dictate the kinematics of the bulk stellar population. Inside it, orbits and velocities are set primarily by the central mass, and any gas that enters this zone must either settle into stable configurations or continue inward toward the horizon. The exact radius of this transition is not sharply defined because the contributions from stars and the black hole overlap smoothly, and different operational definitions can yield slightly different values. However, all reasonable estimates place the inner few hundreds to perhaps a few thousands of light-years firmly under the black hole's dominant influence. In observational terms, the existence of a resolved sphere of influence is crucial for the reliability of dynamical mass measurements. If the region where the black hole controls stellar motions is significantly smaller than the resolution of the data, then models can fit the kinematics with a wide range of central masses and uncertainties grow. In Holmberg 15A, the combination of a very massive black hole and a relatively low central stellar density means that the sphere of influence is comparatively large, improving the prospects for detecting its dynamical signature even with the limitations imposed by distance. This is one reason why Holmberg 15A has become a key system in the study of the most massive black holes, despite being much farther away than many nearer galaxies with smaller central objects. As the inward progression through the galaxy crosses the boundary into this inner domain, the emphasis of the description naturally shifts from the global structure of Holmberg 15A and its core to the properties of the gravitational well carved by the central object itself. Stars' gas and compact remnants that venture into this zone follow paths increasingly governed by the central mass, their high velocities and tight orbits serving as indirect traces of its presence and magnitude, over scales that, while small compared with the cluster, still encompass a substantial part of the galaxy's immediate nuclear environment. As the inward view narrows from the wider sphere of influence of the central black hole in Holmberg 15A toward the very heart of the potential, while the scale of distances and the character of gravity change in ways that are best understood through the framework of general relativity. In this theory, a non-rotating black hole can be described by a characteristic radius, often called the event horizon radius, a distance from the center within which all paths that light or matter might follow curve inevitably inward. The event horizon is not a solid surface but a boundary in spacetime that separates regions from which signals can still escape to the outside universe from those where escape is no longer possible. For a black hole of a given mass, this radius increases in direct proportion to that mass. A simple way to express this is to note that a black hole with the mass of the Sun would have an event horizon radius of only a few kilometers, while one with a mass of tens of billions of suns is inferred for Holmberg. 15A would have an event horizon whose radius is roughly a few tens of billions of kilometers. This is comparable to hundreds of astronomical units, distances several hundred times greater than the separation between the Earth and the Sun, and amounts to roughly about a light day in radius, or a few light days across depending on the exact black hole mass adopted within the allowed range. Even so, this horizon remains tiny compared with the overall size of the galaxy or the cluster. The stars, whose motions are used to weigh the central object orbit at distances of many hundreds to thousands of light-years far outside the event horizon, yet still inside a region where the black hole's gravity is a major influence. Within this inner region, the gravitational field is described not just as a force, but as a curvature of space-time. Test particles, whether stars, gas clouds, or light rays, follow paths called geodesics, which are the straightest possible lines in this curved geometry. For a spherically symmetric, non-rotating black hole, the space-time outside the event horizon has a well-defined mathematical form in which orbital velocities increase as one moves inward, and time intervals measured by clocks near the black hole differ from those measured far away. If a small object were placed on a circular orbit at a radius of a few times the event horizon, it would need to move at a significant fraction of the speed of light to remain in that orbit. The closer the orbit to the horizon, the higher the required speed, until a limiting radius is reached inside which no stable circular orbits exist. For a non-rotating black hole, this innermost stable circular orbit lies at a radius of several times the event horizon radius. Inside that, any object that attempts to orbit instead spirals inward. In realistic astrophysical settings, central black holes and galaxies are expected to be rotating, which modifies these characteristic radii and allows stable orbits somewhat closer in for material that moves in the same sense as the spin, but the overall picture of a steep potential and rapidly increasing orbital speed remains. At the mass scale appropriate for Holmberg 15A even orbits at several times the event horizon radius have periods of only a few days far shorter than the orbital periods of stars in the larger core, which can be measured in millions of years. Close to the event horizon, the gravitational redshift becomes strong. Light emitted from matter in this region loses energy as it climbs out of the deep gravitational well, emerging at longer wavelengths than it had when emitted. A photon produced with a given energy near the horizon arrives at a distant observer with a lower energy shifted toward the red end of the spectrum. The degree of this redshift depends on how close the emission point lies to the event horizon. In the limit of emission, exactly at the horizon, the redshift formally becomes infinite, meaning that no signal from that boundary reaches the outside, which is another way of expressing the defining property of the event horizon as a one-way surface. Time dilation is another aspect of the same geometry. A clock that moves with material near the event horizon ticks more slowly compared with a clock far from the black hole, when both are described in a common coordinate system. In practical terms, physical processes that take a certain amount of proper time near the horizon appear stretched when described from far away. Material in an accretion flow that spirals inward, for example, seems to approach the horizon ever more slowly when its motion is described in terms of the coordinate time of a distant observer, even though in its own proper time it crosses the horizon in a finite interval. These differences in the flow of time, while not directly measured in Holmberg 15A, are part of the standard general relativistic description of all massive black holes and set the context for interpreting phenomena that occur near the horizon in systems where such regions are accessible through electromagnetic observations. The gravitational acceleration near the event horizon is immense. On the surface of the Earth, gravity gives objects an acceleration of about 10 meters per second. Near the horizon of a black hole with tens of billions of solar masses, the gravitational acceleration experienced by a small object could exceed this value by a huge factor, even though the horizon radius is large. The exact value depends on the radius considered and on the frame of reference. But the key point is that the curvature of space-time is still strong enough at the event horizon to severely distort trajectories and to stretch and compress objects along certain directions, effects sometimes referred to as tidal forces. Tidal forces arise because gravity changes with position. In the field of an extended mass distribution, the difference between the pull on one side of an object and the pull on the other gives rise to tides. In the case of a black hole, these gradients can become extreme near and inside the event horizon. For supermassive black holes with very large radii, the tidal forces at the horizon itself can be modest, compared with those near the horizons of stellar mass black holes, because the gradient of gravity at the horizon is spread over a larger distance. However, as one moves inward, the gradients still increase sharply, and any object that passes far inside the horizon is subject to intense stretching and compression. The region just outside the event horizon is where some of the most energetic astrophysical processes can occur, especially in systems where accretion is active. Gas approaching the black hole can settle into a disk that extends inward to roughly the innermost stable circular orbit. As it moves inward, friction and magnetic stresses within the disk heat the gas to high temperatures, causing it to emit radiation across a broad range of wavelengths. The efficiency with which mass is converted into radiation in such a disk depends on how close the gas can orbit before plunging in. For a non-rotating black hole, this efficiency reaches a level of a few % of the rest mass energy of the accreted material, while for rapidly rotating black holes it can be higher. In Holmberg 15A, the current accretion rate appears to be modest, so the nucleus does not shine as brightly as a quasar, but the underlying physical scales and processes of disk accretion are expected to be the same as in more active systems simply operating at a lower level. The enormous mass of the black hole means that even low accretion rates can still inject significant energy into the surrounding gas over long timescales. The size of the event horizon can also be described in angular terms as seen from Earth. At a distance of roughly hundreds of millions of light-years, a horizon with a radius of about a light day subtends an angle on the sky, far smaller than a microarc second, many orders of magnitude below the resolution of current telescopes at most wavelengths. This extremely small angular size means that the event horizon of the black hole in Holmberg 15A cannot be directly imaged with present techniques, unlike the horizons of a few nearby supermassive black holes that have been studied by very long baseline interferometry and radio wavelengths. Instead, its presence and size must be inferred from dynamical modeling of stellar motions, and in principle from any radiation that might emerge from the inner parts of an accretion flow. Even without a direct image, the combination of mass estimates and the general relativistic relation between mass and event horizon radius allows astronomers to assign a characteristic scale to the central object. The result is that deep within the broad stellar core of Holmberg 15A, there exists a region only a few light days across, within which space-time is so strongly curved that light and matter that cross the horizon cannot return, and from which the influence of gravity extends outward to shape orbits over distances of thousands of light-years in the surrounding galaxy core. In studying a system as distant and complex as Holmberg 15A, the picture of its central regions and black hole rests on observations that are powerful yet unavoidably limited, and these limits shape what can be said with confidence and what must remain uncertain. The galaxy lies at a distance of roughly hundreds of millions of light-years, so even large telescopes resolve only structures above a certain physical scale. The broad, depleted core spans many thousands of light-years, which makes it accessible to high-resolution imaging. But the region where the gravitational influence of the black hole is strongest occupies only the inner few hundreds to a few thousands of light-years, and the event horizon itself is smaller still by many orders of magnitude. As a result, the data used to infer the central mass come from integrated starlight and its kinematics within a projected aperture that blends the contributions of many orbits along the line of sight. The point spread function of the imaging system, which describes how light from a point source is blurred by the telescope, and atmosphere must be carefully modelled and deconvolved to recover the intrinsic brightness and velocity structures. Small errors in this step can alter the apparent shape of the central velocity dispersion profile, or the steepness of the inner light gradient feeding directly into the inferred black hole mass. At the same time, the subtraction of the sky background and of diffuse intracluster light adds further uncertainty, especially in the transition zone between the bright galaxy core and the extended envelope. The dynamical models themselves introduce additional layers of approximation. They typically assume that the galaxy is in a steady state, meaning that its overall potential and stellar distribution do not change significantly over the timescales of stellar orbits, and that the orbits can be represented by a large but finite library of possible paths. The geometry is often taken to be axisymmetric or triaxial with simple shapes, even though real galaxies can have more complicated structures. The stellar mass-to-light ratio is usually treated as constant or slowly varying with radius, guided by measurements of stellar ages and metallicities. Yet there may be subtle gradients in the distribution of stellar masses that are difficult to constrain. The dark matter halo is parameterized with functional forms drawn from simulations, but its true inner profile in a dense cluster environment is not directly measured. Each of these assumptions can influence how much mass is attributed to the stars to dark matter and to the central point-like component. In Holmberg 15A, where the black hole mass is very large, the inferred value remains in the range of tens of billions of solar masses across different modelling approaches, but the exact number and its formal error bars depend on how these ingredients are chosen. Degeneracies between parameters mean that different combinations of mass-to-light ratio, orbital anisotropy, and halo concentration can sometimes produce similar fits to the observed kinematics. To explore these degeneracies, modelers vary parameters within plausible ranges and examine how the quality of fit changes. Even so, systematic uncertainties which arise from model assumptions rather than from measurement noise are harder to quantify and may not be fully captured by formal errors. As a result, the central mass estimate for Holmberg 15A is best regarded as an approximate value with significant though not overwhelming uncertainty, rather than as an exact measurement. The structure of the core also contains open questions. The light deficit is derived by fitting a smooth profile to the outer galaxy and extrapolating it inward, then comparing this extrapolation with the observed central brightness. Different choices of fitting function or radial range can change the inferred deficit and core radius. While there is broad agreement that Holmberg 15A has an unusually large depleted core, the precise amount of missing starlight and the detailed three-dimensional shape of the core carry uncertainties linked to these fitting choices. Projection effects further complicate matters. The observed surface brightness and kinematics represent integrals of the three-dimensional stellar distribution along the line of sight, so deprojecting them to recover the true spatial structure requires assumptions about symmetry and orientation. If the galaxy is significantly triaxial with three unequal axes, its projected appearance can differ from that of a simpler axisymmetric system, and some orbital families that exist in a triaxial potential may be underrepresented or mischaracterized in simplified models. This can affect the inferred balance between radial and tangential orbits, and in turn the central mass estimate. The properties of the black hole itself beyond its mass are even less well constrained. Its spin, which influences the structure of space-time near the horizon, and the efficiency of energy extraction from accretion is not directly measurable in Holmberg 15A with current data. The present-day accretion rate is inferred to be low from the modest luminosity of any nuclear emission, but the exact amount of gas crossing the sphere of influence and reaching the inner disk is uncertain, because much of the relevant activity may be hidden or radiatively inefficient. The geometry and strength of any accretion flow on scales of a few to a few tens of event horizon. Radii remain inferred only by analogy with other systems and by theoretical modelling. On larger scales, the interplay between the black hole and the intracluster medium is traced through X-ray and radio observations, but disentangling the effects of past outbursts, current low-level activity and cluster-scale motions is challenging. Cavities in the hot gas, subtle temperature structures and diffuse radio emission provide clues to energy input over time, yet linking these to specific accretion episodes or to a precise feedback efficiency is not straightforward. In Holmberg 15A, as in other brightest cluster galaxies, the existence of a roughly balanced central gas atmosphere suggests that feedback operates, but its detailed history and coupling to the black hole's growth are not uniquely determined from present observations. There are also observational selection effects that shape the sample of known extreme black holes, systems in which the sphere of influence is large compared with the resolution of available instruments are more favourable targets for dynamical mass measurements, so objects like Holmberg 15A with both a high mass and a relatively low central stellar density stand out. Other galaxies may host comparably massive or even more massive black holes, but if their central stellar distributions are different, or if they lie at greater distances, their spheres of influence may be more difficult to resolve, and their central masses may remain poorly constrained. This means that the current sample of very massive black holes is incomplete and biased toward particular kinds of hosts. In addition, because Holmberg 15A lies well beyond the reach of event horizon scale imaging, by current very long baseline interferometric arrays, its horizon cannot be directly seen, and no direct tests of general relativity in the immediate vicinity of its black hole are available. Likewise, gravitational waves from past mergers that contributed to its growth would have been emitted at frequencies and amplitudes that are not yet accessible to present detectors. As a result, many aspects of its innermost dynamics remain inferred rather than directly observed. Despite these limitations, certain elements of the picture are robust. The existence of a large shallow core, the high central velocity dispersion, and the need for a deep central gravitational potential all point to a central mass that is extreme by the standards of local galaxies. The exact numerical value of this mass, its detailed growth history, and the fine structure of orbits and gas flows within the sphere of influence, however, remain subjects of ongoing refinement as observational capabilities improve and models become more sophisticated. In Holmberg 15A, the central black hole and its surrounding core thus stand as a case where the broad outlines of an unusually massive, dynamically influential object are well supported by current data, while the precise details of its properties and past remain partially hidden by distance resolution and the simplifying assumptions that must be adopted when modelling such a distant and complex system.